Welcome, my student, to the second lecture in chapter 24, which is talking about connection or the source connected to the load, either Y to Y connection, or we will connect Y to delta connection. Since we talked about Y connection last class, without talking about delta connection, I will give you a brief about delta connection, then we'll talk in detail about delta connection for next lecture. Here, as a review from last lecture, we have voltage line and voltage phase for Y connection, and similar for the current. There is current line and current phase. We know that in last lecture, voltage line equal root 3 multiplied by voltage phase, and I line equal I phase in Y connection. For delta connection, it is the opposite. Voltage line equal voltage phase, but I line equal root 3 I phase. You can see here, to remind you, we are talking about balanced system. Balanced system mean the impedance for each phase equal the other. Okay, this Z equal this Z equal this Z impedance. Okay, for example, this can be resistor with the inductor, or resistor with the capacitor, or resistor only. Okay, either series resistor with the inductor or parallel resistor with the inductor, similar to the Y connection. Later we will start talking about examples, and if we change the impedance, what will happen for the load, for everything, for the current and voltage. Okay, you can see here the voltage line. From this line to this line, we consider as voltage, we can say voltage line 1, okay, or A, equal voltage phase 1. Similar if it is 2 with 2, voltage line 2 with voltage phase 2. How we said, why we said the voltage line in delta connection equal the voltage phase in delta connection. For example, let us draw voltmeter here, and same thing here, voltmeter in the phase. See this point, it is the same point which is connected to this point. Okay, and here this point for the voltmeter, it is the same point connected to the second terminal in the voltmeter, because this voltage phase equal voltage line, and the current equal current line equal root 3 multiplied by I phase. This is magnitude and this is magnitude, okay, without angle. Later we'll discuss in detail what is the angle here, okay, and here what will be the angle for the current. Okay, we talk about Y connection later, before in last lecture, and how to distinguish between the line voltage and voltage phase. If you remember, between each phase and phase there is 120 degree, and between each line and phase value there is 30 degrees. Okay, but for the current, since they are equal in the magnitude and the angle. Let us start talking about Y connected generator with a Y connected load. This is the source, we will say generator, okay, and this is the load. Consider it is the load, okay. In this example or this section, we will talk about Y source and Y load. You can see here, this is the voltage phase for in the source, this is the current phase in the source, this is the voltage phase in the load, this is the current phase in the load, and in between there is voltage line, between line and line. We connect the voltmeter here. If the load is balanced, the neutral connection can be removed without affecting the circuit in any manner. That is, if Z1 equals Z2 equals Z3. This is what does mean balance. Z1 equals Z2 equals Z3. We can remove line neutral connection. Okay, it will not affect. If it is not unbalanced, we need the neutral connection. Okay, then In will be 0 if you add all the current summation between I phase 1 with I phase 2 with I phase 3. If you add them, you will get 0 value. Okay, you can see here I phase generator equal I line, which is equal I phase in the load. Okay, since it is Y connection in the load. And the same thing, V phase in the load equal E phase in the source. See here, we said last lecture, in the source we will say E, and in the load we will say V. What about if you need to find a current I phase in the load? It will be all your calculation by phase value. Don't use the line value. If you need to find I phase, you divide V phase divide by Z. Okay, you will get I phase. Okay, but if you make a mistake and say E line divide by Z, you will get different value. We will use the phase value to find current phase. Okay, my student. Then if you find I phase in the load, you will say it is equal I load and I phase in the generator. And for V load, V line equal root 3 V phase. Okay, multiply the phase value by root 3, you will get voltage line. Let us take example 24.1. The phase sequence of Y connected generator in figure 24.13 is ABC. Okay, part A, find the phase value theta 2, theta 3. Theta 2, this is the theta 2, and this is theta 3. Then find the magnitude for the line voltages. The magnitude for the line voltage, this is the line voltage. We need to find the magnitude. I think, or let us start solving one by one. For example, find the phase angle theta 2 and theta 3. We know that is ABC sequence. Then the theta 2 will be minus 120, and theta 3 it will be plus 120, or we can say theta 3 plus 120 and theta 2 plus 240, as we mentioned in the last lecture. Okay, for the magnitude of the line voltage, we need the line voltage. We know that we will multiply the phase value by root 3. You can see here root 3 multiplied by phase value, which is 120. See, 120 phase value. You multiply it by root 3, you will get 208, similar to our equipment in the lab. Okay, then EAB equal EBC equal ECA, which is line value for the voltage. Here you can find, see, this and this and this, okay, equal 208. C, find the line current. Line current, which is IA capital A small. How to find this? You will use this formula, since we know that the V phase, which is in the load, voltage in the load, equal the E phase in the source, then VAN equal EAN capital. If you divide VAN, since we have its value 120, by Z, see here, each phase has resistor and inductor, resistor and inductor, resistor and inductor. The value for the resistor 3, and here 3, and here 3. The inductor 4 and 4 ohm, and here 4 ohm. Then for each impedance, the impedance equal 3 plus J40, since it is inductor. If it is capacitor, we will say 3 minus J4. Then 120 and the angle 0, see, it's given, divide by the impedance, you will get the value to 24 ampere. Don't forget the unit when you write the answer. And then the angle minus 53.13. This is for IAN. If you need to find IBN and ICN, okay, you will, this is IAN, this is IBN, and this is ICN, phase value. You will do the same thing here, but for the voltage VBN, which is 120 minus 120 degree divided by 5, same impedance, nothing changed for the impedance. Okay, you will get same magnitude for the current, but different value in the angle. And for last one, ICN VCN divided by ZCN, you will get 24 ampere or angle 66.87. But our question was about line value. Find the line current, not phase current. But we cannot find the line current before finding the phase current. Okay, and Y connection, it is the same, but for the next section, if with the source Y and the load delta, you will find the difference. You will see the difference. Because this, now we can say that IAN capital equal IAN small, which is IAN capital, I line, equal I phase, which is the same value, same magnitude and the same angle. Okay, similar to IB capital B small, which is I line, with I phase, same value, see here, same value, and here 24 ampere 66 degree, 24 ampere 66 degree. Last point, which is D, verify that since the load is balanced, in equal 0. in equal I line A capital A small plus I line B capital B small plus I line C capital C small. If you add them, if you change from phasor form to rectangular form, actually you don't need to change it in the exam. This only for showing that how we get zero value. You add real number with real number, you'll get zero real, and magnitude and the imaginary number with the imaginary number for the each value, you will get the total 0. This means if you add each line with the other line, IA, IBB, ICC, you will get 0 value. And in is the fact equal to 0 as required for a balanced system, since it is a balanced system. Now we'll start talking about Y delta system or Y delta connection. We said that we will work about balanced system, Z1 equals Z2 equals Z3, and we know that voltage phase equal voltage line in general, as we mentioned before in the beginning, and the line current equal root 3 I phase. Okay, we'll study one example here. Example 24.2 for a three-phase system. Figure 24.15. Find the phase angle theta 2 and theta 3. Okay, this is the theta 3 and this is the theta 2. The voltage magnitude for line voltage 150 or angle 0. Voltage for EBC 150 angle theta 2, which will be minus since it is positive sequence. Okay, it is mentioned here. Y connected generator, phase sequence A, B, C. Then this means EBC, the angle here will be minus 120 and theta 3 will be plus 120. See here is the answer. Okay. Part B, find the current in each phase of the load. We need the current here. IAB, IPC, ICA. How to find this? We will divide the voltage across the impedance, which is voltage phase, divide by the impedance. You will get the current going through the impedance. And we know that in delta connection, the line voltage equal phase voltage. This means we will use 115 divided by the value here for each impedance. You will get then the current phase for each phase. See here, they say that phase equal line, okay, and then VAB, which is 150 divided by ZAB, you will get 15 ampere angle minus 53. Similar for IBC, you will get 15 ampere minus 173 degree. ICA, it will be 15 ampere angle 66 degree. For last point, find the magnitude of the line currents. What is the line current? This is the line current. In part B, we found phase load, phase current. طيب, this is the delta connection. We know that delta connection, I phase, if you multiply by root 3, you will get I line. It's easy. We will multiply, only multiply. 15 ampere multiply by root 3, you will get 25. As a magnitude is 25.95. Later we'll talk about how to get the angle here, but this is only to show how to find the magnitude. Okay, and the reference our book, Introductory Circuits Analysis. By this we will end our lecture today, and later we'll talk about delta source with delta load, or delta source with delta or with Y load.